Now the next question is, the TEM wave impinges obliquely on your dielectric boundary with epsilon r1 is equal to 2 and epsilon r2 is equal to 1. So it is related to interface. So here one interface is there, that means media separation. So here one medium 1 I am taking, and this is medium 2. It is having the relative permittivity epsilon r1 is equal to 2 and medium 2 is having the relative permittivity epsilon r2 is equal to 1. The angle of incidence for total reflection is, that is what they are asking. And this particular electromagnetic wave is incident obliquely. So this is the normal to the interface. So with respect to this normal, this incident wave is making some angle. That is called oblique incidence. Okay. So we are not sending normally. So it is making some angle with the normal, means that is called incident, this oblique incidence. Okay. So at this particular criteria, using the Snell's law, we can able to write eta 1 sin theta 1 is equal to eta 2 sin theta 2. Total reflection means this particular angle is 90. This angle we can able to take as the critical angle, like that we can able to take. And eta 1, eta 2 are not impedances in the Snell's law. These are refractive indexes. Okay. So these are given, actually eta 1 is equal to velocity of the wave, okay, in air by velocity of the wave in medium. That is given by square root of 1 by square root of mu1 epsilon 1. And this is equal to, C is nothing but 1 by root of mu naught epsilon naught by, this is square root of mu naught epsilon naught mu1 epsilon naught. Like this we can write. Okay. Now these things will be cancelled. So this entire thing will go to the numerator. So this is equal to this part, that means, sorry, this is a relative permittivity, relative permeability. For many materials it is 1 only, but here we got epsilon r, root of epsilon r. But it is medium 1, so we will represent with 1. Similarly, eta 2 is equal to root of epsilon r2 you will get. Now this entire thing can be minimized to root of epsilon r1 sin theta 1 is equal to root of epsilon r2. So sin theta 1 is equal to root of epsilon r2 by epsilon r1, that is equal to epsilon r2 value is 1 and this is 2. That means we will get 1 by root 2. So this is sin theta 1. So theta 1 is equal to sin inverse of 1 by root 2 is equal to 45 degrees. That's it. So if you know about the Snell's law, you can able to solve this particular problem very easily. The next question is, the plane EM wave is traveling in an unbounded lossless dielectric having epsilon r is equal to 4 and mu r is equal to 1. Relative permittivity and relative permeability are given. Okay. The time average Poynting vector of wave is 5 watts per square meter. The phase velocity is, here they have given power density also. Okay. So what they have given, I am writing here, epsilon r is equal to 4 and mu r is equal to 1 and power density they have given as 5 watts per meter square, and we need to calculate the phase velocity. Okay. So it is also simple thing, phase velocity is given by 1 by root of mu epsilon. So it is equal to 1 by root of mu can be written as mu naught mu r and epsilon can be written as epsilon naught epsilon r. So by substituting these values, 1 by root of mu naught epsilon naught multiplied with 1 by square root of 1 into 4. Okay. This part is exactly light velocity, that means 3 into 10 power 8 by 2, that is equal to 1.5 into 10 power 8 meters per second. That's it. Okay. When a plane wave is incident normally from dielectric 1 onto dielectric 2. Okay. So again the question is related to this two media are separated by the interface. Okay. So dielectric 1, dielectric 2. medium 1, medium 2, and here normal incidence they have mentioned. So wave is a incident like this normally, that is parallel to the normal to the interface. This is the normal to the interface. We have incident like this. Okay. Then because of the impedance mismatch, some part of the wave will be reflected back and some part of the wave will be transmitted into the medium 2. And what they have given, the transmitted wave is, they have given some condition. So transmitted wave is -2 times the electric field of the reflected wave. The electric field of the transmitted wave, that means ET is -2 times of electric field of the reflected wave. This is the given condition. Then they are asking us to get epsilon 2 by epsilon 1. This is the ratio we need to calculate, okay, using this particular condition. So when we use the normal incidence, we have the formula for reflection coefficient and we have the formula for transmission coefficient. So using those formulas, we can able to calculate here. Okay. So what we have, the formula for transmission coefficient, 2 times of eta 2 by eta 2 plus eta 1. Here eta 1, eta 2 are impedances. Okay. Then transmission coefficient, reflection coefficient is equal to eta 2 minus eta 1 by eta 2 plus eta 1. Okay. So 1 refers to medium 1, 2 refers to medium 2. And what they have given according to this particular condition, we can able to substitute. Okay. So I'm writing here, ET means exactly this one we can take. So 2 times of eta 2 by eta 2 plus eta 1 is equal to -2 times of ER. ER is nothing but this one. So eta 2 minus eta 1 by eta 2 plus eta 1. So this one will be cancelled. Then this is -2 times of eta 2. Okay, you can send that one this side. So 4 times of eta 2 is equal to 2 times of eta 1. Like this we can able to write. Okay, then -2 times of eta r we have written. Okay, then it can be written as eta 2 by eta 1 is equal to 1 by 2. Like this we can able to write. Okay. Now eta 2 means root of mu by epsilon. Actually eta means impedance, that is root of mu by epsilon. Mu is equal to mu naught into mu r. Okay, mu r we can take 1 for many materials. So what we can able to get here, root of 1 by epsilon r2 by root of 1 by epsilon r1 is equal to 1 by 2. Okay, so by sending this epsilon r1 to the numerator, you get epsilon r1 by epsilon r2 is equal to 1 by 2. If you square this one, epsilon r1 by epsilon r2 is equal to 1 by 4. But they asked reverse. Okay, so epsilon r2 by epsilon r1 is equal to 4. Even it is epsilon 2, we can write this one epsilon naught epsilon r2, epsilon naught epsilon r1. So epsilon naught will be cancelled. So this ratio is equal to that ratio 1. Okay. Now the next question is, for an elliptically polarized wave incident on the interface of the dielectric at the Brewster angle. Okay, one thing they have given, that is elliptically polarized wave. Next one is it was incident at Brewster angle. What is the nature of the reflected wave? Okay, so medium is there. So Brewster angle means it is related to oblique incidence. So this is the normal to the interface. Okay, so at some oblique incidence we have given, but that is Brewster angle. Incident angle is the Brewster angle. So when you give this Brewster angle, what will happen means either parallelly reflected wave, okay, or perpendicular reflected wave. Out of these two, anything will be zero. That is the meaning of the Brewster angle. Okay, so remaining part will be completely transmitted. That is about the Brewster angle. Now what they are telling about the polarization, we need to comment. This incident wave is elliptically polarized wave. Incident wave is elliptically polarized wave. This wave can be treated like some parallelly polarized wave and perpendicularly polarized wave. But what we are doing, we are sending or we are incidenting this particular elliptically polarized wave at a Brewster angle. By making it is Brewster angle, what you will get in the sense, either this reflected parallelly polarized reflected wave or perpendicularly polarized reflected wave will be 0. So actual thing is, if you incident like this, some part will be reflected, some part will be transmitted, but this in the reflected EM wave also you will be having parallel and perpendicular polarizations. But when you send it to Brewster angle, either this one or this one will become 0. Okay, so either this one or this one is becoming 0 means, for example, you make this is 0. That means here you will be having only perpendicular polarization. Only perpendicular polarization means that is linear polarization. Or if you make this is 0, only parallel polarization will be there. Again, that is linear polarization. Only either you have parallel polarization, or if you have only perpendicular polarization, then we can tell that is a linear polarization. That is what they are asking. This is because if you incident at Brewster angle, so the reflected wave will be linearly polarized wave. Okay, next question. A right circularly polarized wave is incident from air onto the polystyrene having the dielectric constant or relative permittivity is 2.7. The reflected wave. Again, we need to comment on the polarization. You see, one thing you need to remember, we are incidenting this circularly polarized wave. Right circularly polarized wave. They are asking about the reflected wave. Okay, so this thing you need to observe. The direction of propagation is reversed. Okay, you are sending like this, but the reflected wave is in the opposite direction. So surely left will become right, right will become left. So one thing is the reflected wave will be left polarized one. Okay, next. It is not about right circularly polarized wave is incident from air to this particular material. Okay, then we need to comment on reflected wave. And from the polarization concept, if you send this particular circularly polarized wave, then they did not talk about the Brewster angle. So you may have the two components. Okay, you may have the two components. So left only, but because of the two components, you may get elliptically polarized wave. If you send it to Brewster angle, then it will become linear. But they did not mention about the Brewster angle, so that you will be having the two components. Because of the two components, you are getting EP. And because it is right circularly polarized wave is incidented, the reflected wave is in the reverse direction, so that that will become left. Okay, so like this we can able to answer this particular question. Next question. For seawater with sigma is equal to 5 moles per meter and epsilon r is equal to 80. So what they have given, sigma is equal to 5 moles per meter and epsilon r is equal to 80. What is the distance for which the radio signal can be transmitted with 90% attenuation? Okay, at frequency 25 kilohertz. 25 kilohertz. So they asked about how much distance the wave has to travel, okay, with this particular 90% attenuation. Okay, some frequency they have given. So first of all, we need to understand this seawater is what type of material. Okay, so in our concepts we can able to classify the materials using this sigma by epsilon r, this omega epsilon factor. Okay, so it is required to calculate now sigma by omega epsilon for this particular seawater at the given frequency. Okay, so it is equal to sigma they have given 5 by omega means 2 pi, f is 25k, that means 10 power 3 into epsilon is, you can take epsilon r into epsilon naught, that means 80 into epsilon naught value 8.854 into 10 power minus 12. Okay, you see here 10 power minus 3 is there, here 10 power minus 12 is there, that means 10 power minus 9. So denominator is very less value, that means total factor will be very large. So sigma is greater than 1. When you have sigma by omega epsilon is greater than 1, the seawater can be considered as good conductor. When you know the seawater is a good conductor, related equations you need to know. So it is required to calculate about attenuation. That means attenuation constant you are required to calculate. So we have the formula for the attenuation constant, omega root of mu epsilon by 2 into root of 1 plus sigma by omega epsilon whole square minus 1. And now we got the seawater is a good conductor where sigma by omega epsilon is very large. So sigma by omega epsilon is very large means square is also very large. This 1 can be neglected, square and root can be neglected, this minus 1 can be neglected. So out of this one we will get only sigma by omega epsilon. So this is equal to, I can write omega root of mu epsilon by 2, and here I can write sigma by omega epsilon. Okay, send this omega inside, you will get omega square. So what will you get for the alpha? This epsilon will be cancelled, so 1 omega will be cancelled. So finally you will get alpha is equal to mu sigma omega by 2. This is what you got. This is alpha value, okay, for the given seawater. Now what we need to calculate. So generally when the wave is traveling, its amplitude will be reduced. How it will be reduced? Exponentially reduced. So we are talking about the attenuation. So e power minus alpha, for example, you assume the wave is traveling in the z direction, so e power minus alpha z. But this much amount of strength is there after traveling certain distance, that is z distance. Z is the distance we have to calculate. So after traveling this much amount of distance, it will become, how much it will become? 10%. 90% is attenuated means it will become 10%, that means 0.1. We are required to calculate here z value, that means we need to know about alpha value. So calculate alpha value from this particular formula. So mu means mu naught, mu r value is 1, and sigma they have given 5, and omega means 2 pi f is they have given 25k, okay, by 2. So if you calculate this one, you may get at 0.7 approximately. Okay, you can calculate that one for exact thing. Next, that alpha value you can utilize here. We are required to calculate at what distance, that means z value we have to calculate. Okay, so you can able to apply here logarithm. So minus alpha z is equal to logarithm of 0.1. So this is equal to minus 2.3, like that. Minus will be cancelled. Z is equal to 2.3 by 0.7. This is around approximately I am writing 3. Okay. In this way you can able to calculate. So based upon the material only, what type of material we have, we need to change the formulas here. Okay. That is what you need to understand. Next question we'll see. A 50 ohms characteristic impedance line is connected to a load which shows a reflection coefficient of 0.268. Okay, reflection coefficient they have given. So gamma is equal to 0.268, and this 50 ohms is actually characteristic impedance. Okay, if the input voltage is 15 volts, then the net power delivered to the load. Okay, power delivered to the load we have to calculate. Okay, so I am represent that one with the PL. So in order to have this one, first of all we need to have the load impedance. Okay, net power delivered to the load we have to calculate means you need to have load impedance. So load impedance can be obtained using the formula ZL is equal to Z0 into 1 plus mod gamma by 1 minus mod gamma. So this formula is basically coming from gamma formula only. Gamma is equal to ZL minus Z0 by ZL plus Z0. So using that one we can write in terms of this is ZL also. For ZL also we can able to write the formula. You have gamma, you have 50. Okay, that means Z0. So you substitute here. So 50 into 1 plus 0.268 by 1 minus 0.268. Okay, so it is equal to 50 into 1.268 by, here what you will get here 2, this is 3, this is 7, okay, 0.0, like this you can able to calculate. Okay, so it is around 1 point something, so you will get again 50 to 100, in between 50 to 100 you will get some ohms you will get. Okay, that is about ZL, load impedance value. Easily you can able to calculate that one. After getting that, what we need to do now, we need to calculate the total power. power delivered to the load we have to calculate. Power delivered to the load means actually input voltage is 15. How much voltage is going to the load we have to calculate. But out of these 15 volts, some voltage is reflected back. Using this concept, using the reflection coefficient. Reflection coefficient is not 0. If the reflection coefficient is 0, we can tell complete 15 volts is reaching the load. But here, what is happening? This reflection coefficient is 0.268. So, what is going to the load means VL is equal to, we can take this VI into gamma. That means 15 is multiplied with 0.268. That is what we have to calculate. Okay. This is the load voltage, like that we can tell. So now power delivered to the load is equal to VL square by ZL. ZL already we have here. VL we have here. Substitute, you will get power delivered to the load. Okay. So in watts we can able to get this one. So simple calculation you can able to do. I have given the procedure how to do this one. Okay. Next question is, it is desired to reduce the reflection at an air porcelain by use of lambda by 4 plate. Okay. For porcelain, mu is equal to mu naught and epsilon is equal to 7. So this is what they have given. Mu is equal to mu naught. That is nothing but mu r is equal to 1. Okay, relative permeability is equal to 1. And they have given relative permittivity is 7 for that particular material. The thickness of the polystyrene plate required at 10 gigahertz. So frequency is equal to 10 gigahertz. So simply here we have to calculate lambda by 4. That's it. Okay. So lambda is equal to C by F. Okay. So since they have given it is in this gigahertz, and we are going to substitute this epsilon, all those things, farads per meter and henries per meter, we will take C also in meters per second. Okay. So 3 into 10 power 8 by this F value, that is 10 giga, that means 10 power 9. But if this formula is valid for free space. Okay. So I am representing with lambda naught. So how much we will get? It is equal to, it is 10 power 10. If it is going to the numerator, 3 into 10 power minus 2. It is meters. In meters we have calculated. But this lambda we have to calculate in the material what they have given. So this lambda will be changed. So in the material the lambda is given by lambda naught by root of epsilon r. That means 3 into 10 power minus 2 by root epsilon r. That means root 7. So this is what we have to apply. Okay. So the wavelength will be reduced now. Next, what we need to calculate, that the particular plate should be of length lambda by 4. So lambda by 4 we have to calculate. So it is equal to 3 into 10 power minus 2 by 4 root 7. So this is what we need to calculate in this way. Okay. So now you may get doubt. Why they have taken lambda by 4 only? So there is a concept. Okay. Slab in between the two media. For example, here one medium is there. So this is the interface. This is the normal to the interface. We are incidenting the wave. Okay. Because of the impedance mismatch, some wave will be reflected back. Remaining part will be transmitted. This is the wave. This is the criteria we know. Okay. This is the concept already we have. Then here what is the meaning means we should not get any reflections. For that purpose we have the concept of the Brewster angle. Okay. If you incident at the Brewster angle, okay, when theta is equal to theta b, then without having this particular reflections, the wave can be transmitted into completely transmitted into this particular medium 2. This is one way. Another way is we have to use, this is medium 1, this is medium 2, but in between these two some other new medium we have to take. Okay. So in a line way, this is medium 1, medium 2, medium 3. So this is like slab. This slab length must be equal to lambda by 4. Then what will happen means it will observe, okay, it will observe the wave what we have sent. So it will, because of the presence of this one, the reflections can be minimized. Okay. So this is a slab technique is there. This is related to this particular thing. Okay. This slab length must be equal to lambda by 4. Okay. Now the next question is, a transmission line having 50 ohms impedance is terminated in a load of 40 plus J30. The VSWR is. So they have given characteristic impedance na 50 ohms means characteristic impedance, and a load also they have given, that is 40 plus J30, and we need to calculate here VSWR. So to get VSWR, first we need to have gamma L, that is equal to ZL minus Z0 by ZL plus Z0. So that is equal to 40 plus J30 minus 50 by 40 plus J30 plus 50. So it is equal to minus 10 plus J30 by 90 plus J30. So take the magnitude of this one, numerator and denominator, square root of 100 plus 900 by square root of 8100 plus 900. So it is equal to square root of 1000 by square root of 9000. Okay. So it is equal to 1 by 3 you will get. When you get it is 1 by 3, VSWR in gamma we have the formula. Okay. That is 1 plus mod gamma by 1 minus mod gamma. So when you substitute it is 1 by 3, you will get VSWR is equal to 2. Okay. So that is the VSWR value. So the analysis of this VSWR in terms of gamma you need to know, and gamma is to be calculated by using the impedances. Okay. Next one is, in a transmission line, the reflection coefficient at the load end is given by. At the load end is nothing but it is represented with gamma L. Okay, reflection coefficient at load. Okay, that is gamma L is given by 0.3 into e power minus j30 degrees. Okay, what is the reflection coefficient of this particular wave having reflection coefficient at the distance of 0.1 wavelength? That is the question meaning. Okay, so we have to calculate the reflection coefficient at length is equal to 0.1 lambda. Okay, because on the transmission line at a different lengths, this is the load. At this load, gamma L we have, this is what they have given. But now we have to travel at the distance of 0.1 lambda. For example, this is 0.1 lambda distance we have traveled. At this particular place, we have to calculate gamma. Now this is the question. How to calculate gamma of L? That means reflection coefficient at some distance L from the load towards the source. That is the meaning of this one. It is a function of L. It is given by gamma L, that means reflection coefficient at load multiplied with e power minus j 2 beta L. This is the formula. Okay. How to get this one means, just you take the voltage equation on the transmission line, current equation on the transmission line, take the ratio, you will get impedance. Okay. From that, apply the concept of reflection coefficient. That means V reflected by V incident you have to take. That means that current equation we have to write in the voltage equation only. Okay. There you will get the ratio of voltage and the ratio of reflected voltage and transmitted voltage. Then we will get this reflection coefficient formula at different lengths. That is given by like this. Okay. So here you need to concentrate on this 2 also. 2 will be there. Okay. 2 beta L, because it will be like this, e power minus j beta L. Okay. Minus j beta L is coming whenever we have taken the ratio. From the denominator also you will be having the exponential. If it is going to the numerator, like this, here we will get 2 beta L. Okay. So if you know this particular formula, the problem is over. They have given this is 0.3 into e power minus j30 and e power minus j 2, beta means 2 pi by lambda into L. L is nothing but what? They have given 0.1 lambda. Okay, lambda will be cancelled. So 0.3 into e power minus j30, e power, lambda will be cancelled. This is 0.2. That means it is 0.4 pi. Okay. So here 0.3 into e power minus j30 plus 0.4 pi. Like this we can able to write. And here you can able to take, this is the answer. You can able to write this pi, okay, in terms of degrees or in terms of radians. Next, you can able to here negative value is there. By seeing the options, if it is e power minus j, that's it. Otherwise, you can able to take by adding 360 degrees, you can able to get the positive value. Okay, like this you can able to represent the answer. Next question we'll see regarding the antennas. Okay, a dipole antenna of lambda by 8 length. So L is equal to lambda by 8. So it is a less length only. That means we can able to consider given antenna is Hertzian dipole antenna. By seeing the length of the dipole, we can able to consider it is the Hertzian dipole antenna. Has an equivalent loss resistance. Okay, L loss is equal to 1.5 ohms. The efficiency of the antenna they are asking. So efficiency generally represented with eta. So what we need to calculate? Efficiency. So efficiency is given by radiation resistance by radiation resistance plus loss resistance. Okay, so they have given loss resistance, but we don't have radiation resistance. So for the Hertzian dipole, what is the radiation resistance formula? 80 pi square into L by lambda whole square. This formula you need to remember. So it is equal to 80 pi square means approximately I am taking 10 and L by lambda. Okay, L is lambda by 8 and in the denominator again lambda is there. Lambda will be cancelled. It is 1 by 8 we will get. Okay, and that is square. That means 1 by 8. 1 by 8 we will get. So what we can able to write here? This is cancelled. So here 10, 100 by 8 is there. Okay, 100 by 8. So we can able to take this radiation resistance like this only, 100 by 8 ohms. Now take this radiation resistance and the loss resistance, substitute here to get the efficiency. That is 100 by 8 by 100 by 8 plus loss resistance is 1.5. So simply you can able to calculate this particular thing. Okay, just I have taken here pi square. Pi means 3.14. If you square that one, approximately we may get 10 here. That is what I have taken. Next, L is nothing but lambda by 8 by lambda is there. So here you will get 1 by 8. Because of the square in the formula I have taken. Okay, 1 by 8, 1 by 8 I have taken. So simple calculation you can able to perform. Okay. Next one. For an aperture antenna of aperture dimension capital D and wavelength of radiation from the antenna lambda, the far field at a distance greater than, it is just a theoretical question only. If you take antenna and its maximum dimension is D, how at what distance we can able to consider the electric fields and magnetic fields? That means generally we have to consider the radiation or the electric fields and magnetic fields in the far field. The far field will be started if you consider the distance from the center of the antenna. This R must be greater than 2d square by lambda. That's it. Okay, where D is the maximum dimension of the antenna and if lambda is the wavelength that can be calculated from the frequency. Okay, so answer is 2d square by lambda. Next question, a vertical wire of 1 meter length. So length is equal to 1 meter, carries a current I is equal to 1 amp at frequency 10 megahertz. The total radiated power, that is what we have to calculate. Okay, so radiated power, if you want, already current is there, you need to have radiation resistance. So radiated power is actually I square into R radiation, I square R, like that we can define the power. Okay, so I square into R radiation we need. I they have given 1. Actually whenever current is uniform, that is related to Hertzian dipole only or short dipole, what we can tell. Okay, infinitesimal dipole. Okay, that is what we can tell. So here our requirement is getting the R radiation. So again from the same formula, 80 pi square dl by lambda square. So it is required to calculate lambda from the frequency. So lambda is equal to C by F. Okay, because it was given in meters, I am taking 3 into 10 power 8 by, this is frequency is 10 power 7. That means it is 30 meters. Okay, so it is equal to 80 into pi square means 10 I am taking, and L is nothing but 1 and lambda is 30. So 1 by 30, 1 by 30. So like this we can cancel. It is 8 by 3. That is 2. It is 620 means it is 8. Okay, sorry 6. 2.6 ohms. That is the R radiation value. Now we can able to calculate the power. Power is equal to, total power radiated is equal to I square into R. I is 1. It is radiation resistance. It is 2.6. That is 2.6 watts. That's it. Okay. Now the next question. The radiation field of an antenna at the distance R varies as. Okay. It is theoretical question only. If you see, we will be having E theta and H phi. If you take antenna, we have to measure the radiation. Radiation means electric field and magnetic field. In that electric field also, you will not be having all the components. Only theta component will be there, that is E theta. And you will be having only phi component for the H. So if you see these equations, some constant will be there and e power minus j beta R by R will be there. And here also, and here sin theta may be available. Like that, based upon the antenna, this theta quantity will be changed. Somewhere you will get sin theta, somewhere you may get cos of pi by 2 cos theta by sin theta. If you take a Hertzian dipole, that is sin theta will be there. If you take a half wavelength dipole, you will be having cos of pi by 2 cos theta by sin theta. Like that, the radiation pattern shape will be changed. Okay, but here the question is about the distance. So you take any component, in the denominator you will be having R only. That means E theta inversely related to the distance, H phi is also inversely related to distance. So radiation is inversely related to the distance. That is what they are asking. Radiation field of an antenna at the distance R varies as inversely. Okay, that is what we can tell. Next question. Dipole produces an electric field intensity of 1 millivolt per meter. So electric field intensity is 1 millivolt per meter at R is equal to 2 kilometers. Okay, at some distance they have given electric field this much value. What is the field intensity at the distance of 4 kilometers? Okay, at 4 kilometers, what is the electric field intensity? This is what they are asking. For this, again, we need to have the relation in between these two, distance and electric field. Just now I have told the electric field varies inversely with respect to distance. That means, for example, E1 by E2 is equal to R2 by R1. Like this we can write now. Okay, because inversely related, you take it is E1, E2, this is R1, R2. Okay, so we need to have E2 value. So that is equal to E1 into R1 by R2. So E1 is equal to 1 milli and R1 by R2 means 1 by 2. That is equal to 0.5 milli. This is volts per meter. That's it. Like this we can able to calculate. Next question we will see. A transparent dielectric coating is applied to glass having epsilon r is equal to 4 and mu r is equal to 1. So you take one glass material, okay, which is having epsilon r is equal to 4 and mu r is equal to 1. Okay, and we have taken here a transparent coating for this one. Why did we use this transparent coating is nothing but to eliminate the reflection of the red light. Having lambda naught is equal to 0.75 micrometer. To eliminate the reflection. In one of the questions we have seen about this reflection. To avoid the reflection, what is the length we have to take here for this particular coating? Lambda by 4. Quarter wavelength we have to take. So this is lambda by 4. I told about this one. Okay. The minimum thickness of the dielectric coating in micrometer that can be used is. This is what we have to calculate. Thickness they are asking. So lambda by 4 we have to take. Okay. So this side what is there? Air will be there. So medium 1, medium 2, medium 3. This medium 2 is helping for removing the reflections. That is what we need to understand. Okay. So now what we need to calculate in this particular medium, how much amount of lambda will be there, and from that we can able to calculate lambda by 4. That is what we need to calculate. Okay. So, but they have given about lambda naught. Now we need to calculate lambda by 4. So this is basically related to medium 1, medium 2. The reflection coefficient is related to eta 2 minus eta 1 by eta 2 plus eta 1. This reflection coefficient is equated to the reflection coefficient of this medium, these two media. That is nothing but eta 3 minus eta 2 by eta 3 plus eta 2. This is the reflection coefficient related to 1 and 2 media. This is the reflection coefficient related to 2 and 3. So when we equate like this, then we will get the relation among these things. And we need to make reflection numerator is equal, reflection coefficient numerator is equal to 0. From that you can able to get this thickness is equal to lambda by 4. How did we get that one? Means this is the logic you need to apply. Okay. So lambda value we have to calculate using this one, root of mu r. We have lambda naught and we have epsilon r value. Get the value of lambda and get the value of lambda by 4. That's it. You will get the answer. Okay. So in this way we can able to solve this particular question.